today we'll see JPEG, that is one particular way of saving images. So the goal is to save our images and save space, because otherwise they may take a lot of space, and then we want to compress all this information into smaller files without losing quality in our representation. Okay, so that's the goal. So that was this JPEG is coming from this Joint Photographic Experts Group. That is a committee setting the standards for saving images, established by these two organisms. So one is the telecommunications organism, and this is a standard for the international standardization organization. So the JPEG that we will see is a relatively old one, but as in general, what we are seeing is just the basics of this kind of stuff. And that is a newer standard, that is JPEG 2000, and even later I think 2017, but I'm not sure about that one. But okay, so the idea is to get to see some of the ideas related to image compression. So we want to have a good balance between image quality and compression ratio. So you can compress a lot, but then if you lose your quality, then there is no point. And on the other side, if you don't lose quality, but you occupy a lot of space, then again, there is no point. So also, this is important, but it has to be computationally tractable. So that means that you receive a compressed file. When you have to display it, you will have to undo all these operations. So if you have to make a lot of calculations to undo the operations, then that will take you a lot of time. It would be slow. So there are multiple ways of encoding. We will see just the first one, but the standard define other possibilities. And this is the general structure of a encoder and decoder. So all this part is called an encoder. All this part is called a decoder. And then you have the compressed data that may live in a file, maybe transferred through a network, can be, so you have an image, you compress it, you save it or you send it, and then on the receiver, you have to undo the operations that you have done in the encoder. Actually, we will see that the order of operations is reversed. So first, we will see each one in detail, but first you decompose the RGB into luminance and chrominance, then you do a downsampling, then you do you split your images into small blocks, then you do the discrete, the forward discrete cosine transform, then you quantize, and then you encode using this entropy encoder. And then on the receiver, you have to do the opposite. So the last operation was an entropy encoder, so you have an entropy decoder. Your last second last operation was quantizer, dequantizer. Discrete cosine transform, inverse discrete cosine transform. So you do the operations in just the opposite order, the ones that you use in the encoder. And this is a very general, framework. And this structure, encoder, decoder, they're called codecs. So these codecs are this way. And the specific list of steps depends on your standard. So JPEG uses this, but any other standard can use any other arrangement of operations. Okay, so JPEG is based on the discrete cosine transform. It assumes that the source image are images with 8 bits, so they go from 0 to 255. We will see the sequential encoding only. We will have an encoding we will not see the details, but we have seen, you have seen it in the view course. So Guillermo spent some time explaining Huffman. And then, yeah, these two things I will ask you. Okay, so how to check if we are doing well? So we need test images, and this test image, it has a few features that are very nice for checking things with images. So first thing is that we have color gradients. So we have for the 3 channels RGB and also for the intensity, we go from very dark to very bright. Okay, that's one thing. The other thing is this pattern here. So this pattern here has a lot of frequencies. So if you look at the outer part of this disk and you travel in this direction, what you have is a low frequency. You have high and low, then high and low, but the periods are relatively large. As you get closer and closer to the center of the disk, then the frequency is much higher. So you have bright, dark, but now the changes are quicker. So this is a very good way of checking the frequency response of your algorithms. Also, we have fixed a few interesting frequencies. So this one, that is high frequency, low frequency, and these are the same frequencies, but now vertical. And then we have a couple of images. And these couple of images have very different features. So this one is mostly smooth, with a very low frequency almost everywhere except at the edges, while this one has a lot of high frequency almost everywhere. So you have a lot of details and high frequency in this part. Okay, so what we will do is we will compress this image and decode it and see if we see mistakes. Okay, so let's concentrate on this part of the image. So first step in the pipeline. So this was the pipeline. So we will see now each one of these steps individually. So the first step was to decompose the RGB image into a luminance and 2 chrominance channels. And we saw this, I think, in the very first lecture. And it is just a matrix multiplication. So remind this constraint of being mathematically or computationally very efficient. So multiplying by a matrix, this is a very simple operation. So that there is no burden, a special burden by multiplying by a matrix. So this is a very simple operation. And now we have separated the luminance from the 2 chrominance things, channels. And next step is to downsample the color bands. So the luminance stays as it is, but the 2 chrominance, they are reduced by a factor 2. And reducing by a factor 2, also we already saw this thing. We are much more sensitive to luminance than to colors. So if you remove information there, probably this will not be a disaster. How much are we saving? Okay, so let's go backward and make some very easy calculations. So let's say, just to put easy numbers, that we have a square images of size x. So originally we have 3x squared pixels. Okay, so we have to keep 3x squared bytes. Okay, each pixel in each one of the channels, it has a byte. Okay, good. Then we have separated this into 3 parts. One is still xx, but the other 2, they are smaller. They are x half, x half, x half, x half. Then, how much information do we need for this? So we still need x squared, but now we need 1 for this, plus, and these two, they are of the same size, and they are of this size. So this is 1.5x squared. So now we have reduced by factor 2 the size of the image, and probably we have not compromised too much the quality of the image. So in this pipeline, we will do many more things, but even if we stay at this point, so let's say that our encoder decoder is just this step. Is the image, you decompose into luminance and chrominance, you do the downsampling, you forget about the rest, and then in the receiver you do the opposite. You upsample these two channels, and then you reconstruct your image with you invert that transformation. So only with this up to here we have reduced the size of the image by a factor 2. So factor 2 means that you can keep twice.
But why do you have to upsample the chrominance if you don't use information? I mean,
you will lose information. You will lose information. So in this setup, you have lost a little bit of information. But you may remember from the first lecture where we were, or first or second, the one on chrominance and these things. We were reducing by a factor 16, and still we couldn't see in the images. So the chrominance, we are not so sensitive to the chrominance.
so why do you have to upsample? I mean, if you still see the same,
Because
you
have to upsample, because at the end, you need an image of size x squared. So I want to show this one that is a color image. But this is what I have, so I have to put them at the same size. But I have lost information, that's why. Okay, so yeah, very simple modification of the images, and we have already saved a factor 2. So let's see if we can do much better than a factor 2. And the following trick is to split each one of the bands, so the luminance and chrominance bands, into blocks of 8 times 8 blocks. So typical image is 1,000 times, even more, no? Like 4,000, 4,000, let's say. So you're dividing very tiny blocks. So these 8 times 8, they are really small compared to the whole size of the image. So it is like kind of big pixels. But still, in these big pixels, you may have a little variation in them. Okay, so now each image band will be operated differently, independently. Each block within the bands will be operated independently, and we shift the values. So these values, they went from 0 to 255. Okay, so now we subtract 128. So they go from minus 128 to 127. Okay, so we are simply lowering and measuring and putting kind of the mean at 0. The mean value in the range doesn't mean that it is the mean value of the block. Okay, but the mean value of the range, we are putting it to 0. Okay, so now we have blocks that are centered around 0, and we will do the discrete cosine transform. Okay, so the discrete cosine transform, these are, let us think of the Fourier transform. I will use the notation that I used for the Fourier transform in my lectures. Okay, so we have an image. So let's say it is we have a sum over all of this image. But this image is just the 8 times 8 block. Okay, so not the full image, just the block. So we have an image. This is a vector, and I want to produce the Fourier transform for a given frequency. You may remember that these frequencies we have omega x, omega y, and these frequencies are discretized, so they are 2 pi divided by n, and here is 8. This is 8, because we have images of size 8, and then times k, and k was taking values 0, 1, 7. Okay, so this is kx, k, and the same for ky. So this frequency is indexed by k, and we have 8 times 8 frequencies also. Okay, so for each one of these frequencies, we have a complex exponential. So we have the inner product between omega k and r. So this is a function that is defined for the whole 8 times 8 block. Okay, so depending on what is omega k, what the omega k is, that is a vector, you will have different shapes. Do you remember that we were making this kind of blocks where we have black, white, black, and so on? So we have this kind of waves, but actually these waves were the real part of this thing, and this thing we refer to it as phi. Phi that depends on k, and so it is an image. So let's highlight this. So it is an image, and it depends on k. So it is an image that depends on k. And what we were representing, our waves were the real part of these things, because we couldn't represent the complex functions. So we were representing the real part, and they look like these things. So this is the Fourier transform. So the Fourier transform, let's rewrite it again. So the Fourier transform is, you have a basis function, and actually this was the inner product. Do you remember? So it was the inner product between IR and my basis. So between my image and my basis. But my basis depends on like this. So my image, my basis depends on k. Okay, and this one is complex conjugate because of the inner product. Okay, so my Fourier transform is just an inner product between my image and the basis function. If I want to recover my image, So if I want to recover my image, what I have to do is to go over all frequencies and then take this. I will not expand it. I will keep the one, this name for it. So this thing goes there times my basis. So all I have to do is I have this inner product. So these are giving me complex value coefficients, and then I take these coefficients. I have to multiply each one of the bases by the corresponding coefficient. So this was the most general formulation of the Fourier transform. And for the Fourier transform, this basis is a complex exponential, but it has a drawback. These coefficients are also complex, because this inner product is complex. So can I design a basis that is not complex, and that is the discrete cosine transform? So here we have the same. So these are the different files. So these are the different basis functions. And these basis functions, they have a frequency, and we have two frequencies, one in X, one in Y. So here he's using U for the index. I have used KX, KY. It is the same. So they go from 0 to 7, from 0 to 7. And for every combination of 0 to 7, what we have is kind of wave. So for instance, here, you see 0, 0 is no oscillation. It is the same as in the Fourier transform. K equal 1, it is just one cycle in your image. And then K equal 2, K equal 3, and at the end with K equal 7, you have these 4 cycles here. So this is half a cycle. So you have these 4 cycles. So you have white, black, and it was the same in the Fourier transform. So, but only that this is not the real part of the basis. This is the basis, not the real part of the basis. Okay, so how do we construct this basis? So it is this formula here. So this is our basis, and it has the same ingredients that we had. So these are the K's. These are the X and Y. And then all the others are just constants, so we don't care about constants. Okay, so these basis functions, they are, if you look at these bases, it is something that depends on X times something that depends on Y. So these kind of bases, they are called separable bases. So you have a function in general. So if you have a function, that depends on X and Y, but you can decompose this into f of X times f of Y, you say that this one is separable. So our basis is separable. Actually, the Fourier transform basis is also separable. And separable transformations, they have an advantage. That is, you can, in principle, we have formulated everything as a 2D, transformation. So for doing these calculations, it seems that I have to go, how to say? So I have to go over this one here to do the Fourier transform. I have to go over the whole image and then do something for the whole image. So that is a 2D operation. But separable functions, they have an advantage. That is, first, you can do some operations in one direction, then you will have a new image. So you have your image, you do kind of Fourier transform in 1D, Fourier transform in 1D, and then this is somehow distorted. I don't know how it looks like. It is partly in a space. So in one direction is frequency, but in the other direction is a space still. And now you do another operation. Let's do 4 operations. Let's use different color. Now you do the operation, the 1D transform in the vertical direction. And now you have your 2D Fourier transform. So now you have something like standard Fourier transforms. So 2D separable transformations, they have this advantage. You can decompose into row and column operations, and they are very cheap. So when you reduce dimensions, so when you go from 2D to 1D, things become very, very quick, cheap. And here we have an example. So we have reduced in one direction by a factor 2, but in 2 dimensions, it is reduced by a factor 4. So the more dimensions you have, the more savings you, so this is for 2 dimensions. If it is n dimensions in general, and you reduce by a factor 2 in each one of the dimensions, and you have n dimensions, you have a reduction by factor 1 to the 2 power n. So making things separable keeps operations very, very cheap. Okay, so the fact that the cosine transform is separable, it also keeps the computational cost pretty low. And this one is just the discrete cosine transform, and we see this structure. So this lambda is just a normalization factor to make the basis to be unitary. Okay, so that the norm of the basis is 1. The norm of the basis is, these are images, right? So you can compute the same way that we are computing this kind of inner products. You can compute the module of the basis. The module of the basis will be 5k r times 5k r. This is just the standard definition of module. So, and you want this to be 1, and to be 1, you need these extra factors in flow. Okay? But these are these extra factors for unit basis. And then otherwise, what we see is the basis times the image. This is the inner product. And you are summing overall space. So all this is just the inner product of the image, the block that is 8 times 8 times the basis function. And this will be the coefficient that you have in the discrete cosine transform. So, yeah, this is an example of how it would look like. So, this basis is separable. So, that means that we have a wave in x and in y and a wave in x. Okay, now we multiply the two. Multiplying the two gives us this thing. So, this is the basis. Now we have the image. The image is whatever it is. So the real image that we are compressing. And now we multiply the two. This is this inner product. So we multiply the two. This is what we get. And then we sum. So we sum everything will give us a single number. That number goes there. Why? Because this is for k, x, k, y equals 4. So kx, ky for 4 means that the Fourier transform for this k is this number. It's this number that goes there. And you do the same for all the k's, and at the end, this is how the discrete cosine transform looks like. And it has the same kind of interpretation as the Fourier transform. In the Fourier transform, low k's were associated to low waves, to slow waves. So these are low frequency components. High k's, they were associated to high frequency components. So here it is the same. And what happened in the Fourier transform? So in the Fourier transform, we were saying the power spectrum of images, in general, many natural objects. I will do it in 1D. But the Fourier transform of images, they behave like this. So they behave like 1 over omega squared. So that means that most of the energy is at low frequency. So in the discrete cosine transform, it's the same. Most of the energy is at low frequency. So the low frequency components, they tend to have higher values than the high frequency components. Is it more clear now, the formula that you were asking? Okay, so now we have all the pieces. We do the discrete cosine transform for all these pieces. This is just another representation of this thing. Same, all these are the same thing. So there's nothing new. Okay, so we have done the discrete cosine. Yeah.
I don't get why we are dividing each one into
blocks of 8.
Yes, because you have, I mean, they are smaller, but you have many more images.
That's a good point. Okay, so let's say, let's do it with simple numbers. Okay, so let's say that I have, I don't know, 1,000, an image that is 1,000. Okay, so I have 1 million pixels. I have to do whatever my operation is, will involve about 1 million multiplications, for instance. Now I divide this into small blocks, 100 blocks of size 10 times 10. So how many blocks do I have here? So I have 100 times 100 blocks. So this is the 10 to the 4. I have 10 to the 4 blocks. And each one of the blocks is of size 10 times 10. So this is 10 to the 2. So each one of these operations that I do here, they're much cheaper. They only involve 100 multiplications, but they have to do 10,000s of those. But at the end, the complexity is similar. So I don't mind doing some operation on the whole thing that involves 1 million numbers, or doing 10,000 times some operations on very small images. It is true, I have 10,000 of these small images, but the complexity is the same. The amount of numbers is the same.
You have those operations 3 times, right?
Sorry?
You have, those operations are performed 3 times. Because you have 3 numbers.
Yeah. So you have 3 channels. So I'm talking just about the channel. And that is for linear operation. So I have 1 million numbers, and I'm assuming that my transformation involves 1 billion operations. But there are operations whose complexity is not. You have seen this thing of O n squared, O n log n. You have seen this kind of stuff? Okay. So if my operation is linear, then I don't mind doing it on the whole thing or doing it on small pieces. Okay. What happens if my operation is n squared? And there are many of those. So for instance, matrix multiplications of this kind, a naive Fourier transform, the discrete Fourier transform, naive one, is also of this kind. Why is it of that kind? Because I have, where is it, my Fourier transform? It is here. So for every coefficient, I have to do, let's use a different formula. So these are images of 8 times 8. So this involves 8 times 8 operations. But I have also 8 times 8 coefficients here. So for each one, I have 64 coefficients here. So I have to multiply this thing by this. So if this is n, if this is n, this is also n, and a naive implementation of this is n squared. It's a complexity of n squared. Okay, so the Fourier transform, a naive implementation of the Fourier transform is also n squared. Okay, so let's see if we are saying something. Okay, so let's say that I have 1 million pixels. So if I have 1 million pixels, what is the complexity of doing a Fourier transform, a naive Fourier transform? Will be 10 to the 6 squared. So this is 10 to the 12. Now, let's say that I do 10,000 Fourier transforms, but now each one of these Fourier transforms is only 10 squared. So now the complexity is 10 to the 4 times 10 to the 4 is 10 to the 8. So now this is 10,000 times cheaper. So it depends on what is your operation. For linear operation, it doesn't matter. You can do it on the whole thing, or you can do it in small pieces. If you have quadratic operations, it is much cheaper. And also for these ones, it is cheaper. If you do the calculations, it is cheaper. If you do it in small pieces. Okay, good. So we have our pieces, and I think it is a good point to make a break. No, we are going to 30, okay, to half an hour. Because I don't want to break in the middle of a quantization. Okay, good. So then, now, let's say I have this discrete cosine transform. For the moment, with the discrete cosine transform, I haven't lost any information. So, given the piece, I have the discrete cosine transform. Given the discrete cosine transform, I can recover the piece. So it is simply to do the inverse discrete cosine transform. So I haven't lost any information yet. And now we will try to reduce this. The amount of information that we have in each one of the channels. So now the discrete cosine transform, we will quantize them. So instead of saving the transform, we will save the transform divided by something and rounded. And then we have quantization tables for that. So we will not divide. Why this is saving information? Okay, so let's say that in general, for each one of those coefficients, this is one of the coefficients of the discrete cosine transform. I need 8 bits. Okay, so I need 8 bits to represent that number. But now, so this is a number cosine transform. So let's call it I. So this is my at some particular frequency. Okay, so now instead of that, I will divide this, let's say, by 2. I divide it by 2. So this can go from 0 to 255. If I divide it by 2 and round, now this can go from 0 to 127. And I don't need 8 bits anymore. I need only 7 bits to do this. To save these numbers. And if you divide by 4, then you need 6 bits and so on. Okay, so I'm saving, so for instance, how much information I'm saving here, how much space am I saving? It is 1/8, okay, because we are going from 8 to 7, so you are saving 1 bit, 1 out of 8. Okay, so yeah, this is 12%. This is 12%, 12.5%. So before we did the reduction by 50%, now by saving 1 bit per coefficient, we are saving extra 12% of the size. But we will not divide by 2. So we will divide by this table. So some of the coefficients we will divide by 2, but some other coefficients we will divide by 12. So that means that here we are saving 1 bit, here we're saving between 3 and 4 bits, because it is between 2 to the 3, 2 to the 4. So, and each coefficient is quantized in a different way. So some coefficients are divided by 2, some other coefficients are divided by something else. And let's look at the two tables. First thing, numbers here they are larger than numbers here. Why? These are for the chrominance, this is for the luminance. Because we are less sensitive to chrominance. So we can remove more bits from the chrominance channels. Another observation, if you look at these numbers, this what are they? That is one that is very visible. This is it here? Where is it? Is it here? Yeah, this quantization table. If you look at this quantization table, you see that we have 1, 1, 1, while in horizontal, while in vertical we have 1, 1, 2. So that means that we will lose a little bit more information here in this direction. Maximum here is 10, maximum here is 14. So we will lose more information in vertical than in horizontal. Why is that? Again, because of our visual system. Our visual system has much more resolution in this direction, in horizontal, than in vertical, because we normally look at our same height. So, yeah, so we have the discrete cosine transform. So this is the cosine transform of the patch. So we have a block of 8 times 8. This is its Fourier transform, its cosine transform. And then this is the quantization table. So we divide this by this, and we keep it there. And now you start to see that all these numbers, many of them, they start to be very low. How many bits do I need to represent a number that is between 0 and 1? Just 1 bit. Or 0 and 1 and 2, just 2 bits. This one I will need 8 bits. This one I will need 5 bits, and so on. So now we start to see the trick. Not all numbers will use the same number of bits. Okay. So this is again very interesting. Why dividing in 8 times 8? One reason is this complexity. But there's another reason. They act as a small or kind of bigger superpixels. So here you have tiny pixels. Now, let's say that you divide this into blocks of 8 times 8, and you keep only the DC component. You keep only one coefficient, only one, just this one. You keep it what it is, all the others you set to 0. Okay, so we have, how much have we saved? So it is not that we are, so we had originally in the discrete cosine transform, it was an 8 times 8 block. We are keeping just one pixel. So it is a saving of 63 divided by 64. We are removing 63 coefficients out of this 64. So this is a huge compression, and still we see very low quality, but we see something there, and it is relatively well. It represents very low quality, but we can see more or less what it was there, and we have done a huge compression. Any question up to here?
Yes. So we just do the first pixel.
Yeah.
And
First, not first pixel. First, discrete cosine transform coefficient.
how do we do all those operations if we just pick one pixel?
Yeah, just to show that even if we do a huge compression, still we can see something. So in the next slides, we will not be so harsh. Okay, so yeah, but if we are very harsh, still we can see a little bit what the image looks like. Okay, so now let's make the break. So we are here. Okay, so even if we use just one component, we get something that approximates the original image. Okay, good. Let's look at this ugly face is a special case, but let's look at this one. So if you look at this one, and you divide this image into small blocks, and each one of these blocks, you approximate, you just consider the DC component, so the 0, frequency coefficient. So you would see that the first pixel, okay, so it is what it is. So this first block, it is what it is. But the second one is very similar to the first one. And the third one is very similar to the second. And that happens for most of the blocks, except when you reach the edges. So at the edges, you will have big jumps, but otherwise, it is very smooth. So if it is very smooth, so that means that in general, for these coefficients here, for the 0, coefficients, in general, you will need 8 bits. But if you look at the difference, you don't need so many. So the DC components, the 0, frequency components, they can take the value they want. But if instead of the components, you encode the difference, so you keep the first one, and then the second, you give what is the difference to the first one, and the third, you give what is the difference to the second. The information is the same, so you can recover from these differences, you can recover the original signal. But now, because the differences tend to be small, all these differences will tend to be around 0, most of them. So that means that instead of sending the DC components, you will send the first DC component and the differences between second and first, third and second, fourth and third, and so on. So this is called a differential PCM. PCM is a way of encoding digital signals. So the idea is that you compute the difference with the previous one. And you will separate the encoding of the first component, so these coefficients. So these coefficients will be encoded in one way. All the other coefficients, the AC component, this alternate current component, so the frequency components, they will be encoded in a different way. So the DC components are done with a differential PCM. And you see that the idea is that the differences require fewer bits because they are closer to 0. Now for the AC components. So the AC components is all the others. So these, they go with PCM. All the others, they will go this way. Okay, so the first thing is that we have said low frequency components tend to have more energy. So even if they all have some frequency different from 0, but these coefficients here, they will tend to have more energy than these coefficients there, especially after quantization, because in the quantization, we have penalized much more the high frequency component. So originally they had fewer energy, and also we have penalized them more, so they have even less energy at high frequency. So we will go through these components following this path. So let's say that this is our block, DCT block, so the coefficients of the cosine transform, and then this is number 23. This is the first one in our list. Then we go to this one. This is 2319, and then we go to this one, that is 29, and you go doing a zigzag on this DCT block. So in this list, because of this property that low frequency components tend to have more energy and they have been less penalized, these numbers will tend to be larger than these ones. Okay, so now we have our zigzag, and now that sequence, that list of numbers, we will convert them to a list of symbols. And the first symbol is always a rank length and size, and the second symbol is an amplitude. So we will see what each one of these means. So for the rank length is here. We have not seen it, but there will be here. It is not a very good example, but there will be sequences of zeros. So there will be many zeros in here in this list. Okay, so in this example, there are not particularly many, but in general, there will tend to be many zeros there. So what we will encode is the number of consecutive zero values, and they go from 0 to 15. So this means that we are using 4 bits to represent how many zeros are ahead. And then the number of bits used to encode the amplitude. So not all, because not all these numbers, have the same amplitude. So these numbers tend to have more amplitude than these ones. So we will not use the same number of bits for all of them. So we have to say the next one. So we have 0, 0, 0, 0, 0, and then a number. How many bits have you used to encode that number? And then you will have the quantized value. Okay, so let's see. That is for the AC. In the DC, the structure is a little bit different. So rank length is not included, and then we simply say what is the size and what is the amplitude. Okay, so let's say that you use just 1 bit. So with 1 bit, so we have encoded the zeros in the rank length. We have said 0, 0, 0, 0, and then the next one is not 0 for sure. So with 1 bit, which are the numbers that you can represent? You can represent these two values, -1 or 1. You don't need to represent 0, because 0 has already been accounted by the rank length. Okay, so now with 2 bits, I can represent 4 values, but I don't need to represent -1 and 1, because if I need to represent -1 and 1, I use only 1 bit. So if I need to represent the number that is any one of these 4, -3, -2, 2, or 3, I could use 2 bits, and then I have my table here of amplitude, and I would say, okay, so these are the 4 values that I want to represent: -3, -2, 2, 3, and then I say this is 0, 0, this is 0, 1, 1, 0, 1. So with 2 bits, I can represent all those numbers. So now, 0, 0 is not the standard representation with 2 bits of -3. Okay, so this is a different kind of encoding to just binary encoding. And with 3 bits, I can represent 8 values that will be these 8, and I don't need to represent any one of these because they have already been accounted by codes of different length. And then I can really efficiently use my bits to represent all these numbers. So now, with all these tricks, we have seen a few of the tricks, there are many more tricks, but with all these tricks, what can we achieve? So you are familiar with JPEG images. So you look at the JPEG image and normally it looks good. Okay, so how much information are we losing? What is the file size? So let's say that I keep the whole data, so everything, all the bytes that are there in the raw image. So in the raw image, we don't have the size, we don't have the raw size here, so we cannot compare to not compressing at all, because even this one is JPEG at 100% of quality. It is making some compressions. Lossless compression, so we don't lose any information, but I still compress. So we cannot compare to the raw data, but we see that without losing anything, we have a file that is 700 kilobytes, that is here, so 660 kilobytes. And as we apply more and more tricks, and our quantization tables are even stronger, so they penalize more and more coefficients, the file size decreases. But even at zero quality, so zero quality, you have a relatively good image, and you have reduced the file size by a factor of 10. So with only 10% of the data, I can represent something that is of sufficient quality depending on what is your purpose. So for, I don't know, for just taking a picture and sending on WhatsApp, I don't need 700 kilobytes, but only 64 kilobytes. But it depends on what is your purpose. You can really reduce a lot by applying these kind of tricks. Okay, so yeah, this is if you want to look into a JPEG file, you can use this program, and there are many other programs. And the thing is that, for instance, let's say that you have this JPEG image, you inspect it. Okay, so this is general nearly all image formats. So we have been discussing a lot on the content. So we have been discussing on the content. So how to code the content so that we save space. But besides the content, there is a header. And this header tells you things about the content. So for instance, it tells you my image is of size 1000 times 1000. And it has 3 channels. It has R, T, and B. And it has, I don't know. So it tells you things about the content. So in general, these things are called metadata. So this is the data, and this is the metadata. Metadata is a description of the data content. So let's say that you have a file. So you have a file in this, and it is this is a JPEG file. Yeah, now that we understand all these kind of tricks, we see that JPEG specifies how to write the content. And we have some other way of encoding images, GIF images, for instance. But the way to specify the content in GIF is different from the way to specify the content in JPEG. And let's say that I take this file and change the extension to GIF. How can I know that this is wrong? So if you tell me now that this file is GIF, how can I check that that is true? Or the opposite, if you tell me now that this file is JPEG, and I have seen this, okay, so you have to change a JPEG file into a GIF file, and then you simply change the file name. That doesn't work, because the way to specify the content is different in both standards. So how can I know that this is incorrect, that this is not true? It is through the header. So in the header, I have to make some, I have to leave some marks that tell me that that is a JPEG file. And this is the first one. The first one is a stack of image. So all JPEG files, they start with the 2 bytes FFPA, all of them. So if you look at the metadata at the header, the first 2 bytes are FFPA. And now you know it is a JPEG file because it has this label, and each combination of bytes, they have a particular meaning. So this one is the start of image. Okay, and then we have many other labels. So we have start of image, we have end of image. So the very last file, the very last 2 bytes, then we have the content FFD9. This is a hexadecimal. So, and then we have labels for defining our stuff. So we will define frames. We have not gone into what a frame is. We can define Huffman tables, but again, we have mentioned that at some point we may use Huffman encoding, and if you have a Huffman encoding, you have to give the Huffman table. You can embed your quantization tables, so not all images are quantized in the same way. So the quantization table has also to go in the metadata. Yeah, so many other different labels. Even this one, that is a comment, so you can make comments and put them in the metadata. And then if you look at the file, so you see the first 2 bytes, so an offset of 0 with respect to the beginning of the file, we have this FFP8. And then the next 2 bytes, are FFEB, that is up 13. And we can look for what up 13 is. Because FF, sorry, I don't have it there, no? Yeah, up 13, so it is here. So up 13, and it is application specific. And application specific, in this case, it was Photoshop 3.0. So Photoshop is putting FFED, but some of the program is putting something different in there. And then you keep adding more and more labels, flags, tables, whatever. And at some point, you will go to the data. So here you have the quantization tables, for instance. And at some point, you will reach so these are the Huffman tables. You see the Huffman tables. You also here see start of a scan. So start of a scan is the data itself. So at some point, so you have a lot of labels, quantization tables, whatever, and at some point you will have a flag saying, okay, so here starts my data, and now you have the whole content. And this is a structure that is common to many different file formats, image file formats. So you have a header with metadata, and then the content. And the way to specify the content is different for each one of the stuff. Okay, so this is the main message here. And if you are very clever, then you can compress your original data from big sizes to small sizes without compromising the quality. So that is all. No? Okay, so